Okay, welcome back. Today we're going to talk about elements, compounds, and mixtures. Okay, anything that you can think of, any material, substance, etc., is made up of matter. Matter, by definition, we would say is anything that has mass and takes up space. So if you can find its mass, or it has some mass to it, and it has a volume, it takes up space, that would actually qualify as matter. Okay. Now, when we're trying to classify our matter, we can actually split it into two categories. We can either say we have a pure substance. A pure substance is made up of only one ingredient, one thing, okay? Or it's a mixture, which would be two or more different ingredients kind of mixed or blended together, okay? Now, let's go back to pure substances. There's really two categories for pure substances. There's elements, and when you think elements, you really should be thinking periodic table. And you look on the periodic table, things like copper, zinc, iron, magnesium, chlorine, hydrogen, mercury, things like that, all on the periodic table. Those are elements. Okay, water is not an element, right? Because water is not on the periodic table. So pure substances, elements, just see the periodic table. Those are your examples. Okay. Now, for me to show you a couple things visually, here is a sample of sulfur. In case you haven't seen sulfur before, it looks like a yellow rock. It doesn't smell very good. Something like aluminum foil, like just aluminum, that's a good example of an element. Something like bromine, you maybe have never seen this before. This is a liquid at room temperature. It's kind of a brownish liquid. It turns to a gas pretty easily. This is actually pretty toxic, so I got to be careful with it. But that's bromine. Bromine is one of the two elements that's actually a liquid at room temperature. The other element would be mercury. That's also a liquid at room temperature. I'll give you another example, copper. Okay, it's just a strip of copper. And if you're thinking, well, what about a penny? Here's the catch. Sometimes you're thinking, oh, that's just copper, but it's actually a mixture of metals. We'll get to that in a minute, okay? So again, first category of pure substances, elements. Second category is sometimes we have compounds. When two or more elements chemically combine, when we say chemically combine, we mean atoms that are bonded together. Give you some examples of that. Maybe you're thinking sodium chloride, NaCl. Sodium and chlorine are both present in this substance. The sodium ions and the chloride ions are kind of chemically connected or bonded together. This is considered to be one substance. Okay, so that is a pure substance, but it's a compound because it's made up of two or more different elements. Something like baking soda, which is sodium hydrogen carbonate, is made up of, you can kind of look at the elements, sodium, hydrogen, carbon, and oxygen all make up this, but the pieces would be molecules would be sort of the same across the board, and therefore this is considered to be a pure substance, right? Something like table sugar, sucrose, okay? The formula here, C12H22O11, every molecule of sucrose has 12 carbons, 22 hydrogens, and 11 oxygen atoms that are all chemically bonded together. So one piece or one unit, a molecule of sucrose would all look the same. Okay, so here's an example of, again, pure substance. Something like copper sulfate, maybe you've seen these before. They look like little blue rocks, kind of like what's in your fish tank, but what's in your fish tank, the blue rocks, that's not actually copper sulfate, because this will actually dissolve in water. Made up of copper, sulfur, and oxygen, right? Okay. Now, so everything that's a pure substance either fits into the category of it's either an element or it's a compound. Okay. Now, sometimes we have mixtures, two or more different substances. And there's actually two categories mixtures can fall into. We can have heterogeneous mixtures, where it's not very well mixed, and the pieces are, you can actually see the different phases or different substances involved in a heterogeneous mixture. Hetero means different, so it's different enough that when you visually look at it, you can tell it's a mixture. I'm going to give you an example of a heterogeneous mixture. Okay, if you look at this little bag here, this is a bag of sand, and you can tell that some of the pieces look different than the other pieces. Therefore, when you look at this, it's made up of different substances, and it's definitely a heterogeneous mixture because you can see the difference. Okay, now give you a couple other thoughts here. We've got pure water. Okay, this is not tap water. Be careful, because sometimes tap water, it has things dissolved into it. You can't tell it's a mixture. But in this case, we have water, okay, pure water. And then I have some vegetable oil. And what I'm going to do is I'm going to mix them together. So let me pour my water in here first, okay? And then I pour my vegetable oil in here. And if you look closely, you can tell that this is a mixture, because my oil is up here and my water is down there. Different colors, different substances. When you can visually see that you have two or more different substances, that's considered to be a heterogeneous mixture. Now, homogeneous mixture means you're looking at it and it's so well mixed, the particles are so uniform that you actually cannot tell it's a mixture. So to give you some examples of that, when you actually get table salt, you typically get it out of a container that contains more than just sodium chloride. It also has sodium silicoaluminate in it, which again, you can't tell by looking at this that there's more than one substance. So therefore, it would be considered what we call homogeneous. Homo means the same. So all the particles are the same. You can't tell. Something like Tums, little Tums tablets, main ingredient there is calcium carbonate, but there's other ingredients that go in with it, but you cannot tell it's a mixture. Okay, back to my example with a penny. You're looking at this going, well, I think a penny is mainly made of copper. True. There's zinc also in here, and it's a mixture, but it's mixed to where you can't see it. Now, if we were to cut a penny open, you actually could see the outside has a pretty significant copper layer compared to the inside that was zinc. If we were to cut through this and open it up, you'd actually be able to tell that it's a mixture. So sometimes it's a matter of looking at your substance and actually trying to figure out, can you tell it's a mixture or not? That's kind of where we're going to stop for a moment. Okay, now we're going to talk about elements, compounds, mixtures at the particle level. When we think in chemistry, a lot of times we are thinking in terms of atoms and molecules and so on. So frequently we potentially will use the model kits, and I've got kind of a large version of it here, and pretty much these circles, these spheres actually represent different elements. They purposely are different color to represent different element. This one, the red one, typically we say represents oxygen. It has two holes in it because typically oxygen bonds in two places. Something like the green one, usually used for halogens or chlorine. That is only one hole because it bonds in one direction. The white ones we typically use for hydrogen. These represent hydrogen atoms. They're not technically hydrogen atoms, but in science, a lot of times we try to come up with models or representations, and so that's why we use these model kits. The blue ones are for nitrogen. The carbons are the black ones are for carbon. 4 holes, because typically carbon likes to bond in 4 places, right? Yellow ones, sulfur, and you get the point. Different colors, different elements. So I have a couple examples here on the board. I've got a purple, a green. One thing to notice here, there's 2 brown ones connected together, 2 white ones connected together, and this is just an element. Why it's just an element is because we have 2 of exactly the same thing connected to each other. So all the elements in that particle or molecule are the same. Therefore, we would call that just an element. Same thing here. Typically, I don't have the brown ones out, but I have 2 red ones. 2 red ones connected together, we will call this a molecule. This is oxygen. You think of things like oxygen as O2. It's because it's a diatomic molecule, right? Hydrogen, 2 white circles connected together with a single bond. This is a molecule of hydrogen. Still just an element, even though there's 2 of them, right? And you might remember there's a list of diatomic elements: hydrogen, oxygen, fluorine, nitrogen, bromine, iodine, chlorine. Those are all elements that tend to bond with each other, or bond with themselves and form diatomic molecules. But they're still technically just an element. The smallest piece, just an element, right? And then we have compounds. Compounds is when we bond 2 or more different elements together. So I've got an example here of one of the brown ones and one of the green ones connected together. Model kit here, I've got a hydrogen connected with chlorine, HCl, hydrochloric acid. That is just a bond. The smallest piece of this substance is a molecule, but because there's two different elements in it, these are chemically connected or bonded together. Now, how do I separate compounds back into the elements if I wanted to go back to just chlorine and just hydrogen? You have to break these chemical bonds. Okay? So the only way to separate a compound back into its elements is you have to cause a chemical change by breaking chemical bonds, right? Some other examples, this we usually use typically to represent water. It's oxygen with 2 hydrogens attached, okay? Nitrogen with 3 hydrogens attached. I have a couple drawn up here on the board, the NH3 molecule, the water molecule, H2O, and I have some little models also that represent this. These are magnetic. Now, with ionic compounds, sometimes it's a little bit more complicated. Ionic compounds actually don't form molecules, individual pieces. They actually are just a network of repeating pattern of sodium ions bonded to chloride ions, bonded to another sodium ion, and so on. So this just kind of represents the chlorine in green, the sodium in blue, and it's just the sodium and chloride ions bonded to each other, and it would be a 3-dimensional picture on this. So we don't really usually go through and try to isolate one sodium and one chlorine. However, when we write formulas, ionic compounds, we typically do give the ratio of sodium ions to chlorine ions or chloride ions. So that's why you see like NaCl. But there isn't such thing as a molecule of NaCl. We actually call it a formula unit. Okay, so ionic compounds are a little bit more challenging. We don't really use the model kits typically for those, but I've got kind of this magnetic model here. Okay, now putting this all together into mixtures, if you look at this picture up here, okay, first of all, can you tell it's a mixture? Okay, visually, yes, you can, because we're looking at representing different substances with different colors or different types of pieces, right? So we've got 2 different substances showing up in this box. We've got the brown where they're diatomic, right? So that's one substance, all the same. And then the green ones must be a different substance, okay? Now, if we were to say, is this a mixture of elements or compounds or elements and compound, you should be able to look at this and go, hey, that's an element, hey, that's an element. So this is just a mixture of elements, right? So all the pieces in there would be representing 2 different elements, right? This one here, can you tell it's a mixture looking at it? Absolutely, because we've got these pieces, and we've got 3 of them in there, and then we have the purple pieces is a different substance. Looking at this, it's a mixture. What type of mixture is it? If you look closely, you've got a compound here, 2 or more different elements chemically connected together. That's a compound, but then this is just an element. So we would say it's a mixture of compounds and elements, right? Now this third one over here, I just want to look at this for a second. This is sort of my magnetic model. This is sodium chloride and the water molecules. And if you look at this, first of all, you would classify this as a mixture of compounds, right? Because it has 2 different compounds. It has water and it has sodium chloride. Now, we usually don't spend a lot of time talking about heterogeneous and homogeneous at the particle level, but if you look at this, there's definitely a separation between the water and the sodium chloride. You throw some salt in water, salt sits on the bottom. So you would consider that, if you can see the differences visually, you could call this a heterogeneous mixture. However, over time, what happens is the water molecules will start to surround and pull off the sodium ions. The oxygen actually surrounds that side, and then the chloride ions get pulled off and surrounded by the hydrogens. And what happens over time is this all tends to spread out, and you end up getting everything dispersed. So when you stir up your salt water, over time you can't see the salt anymore. Then it becomes a homogeneous solution, okay, or homogeneous mixture. All right.